This is the walkthrough video for PCTC 2023, question 10, find and destroy. Okay, so we're given this grid, and we essentially need to identify where is the rectangle of a certain symbol that isn't just dots. And then we need to, once we identify that, we then need to get rid of it by replacing it with dots and then printing out that grid. And then we're given loads of different rules and constraints and stuff like that. Okay, so this question is actually pretty difficult. And the crux of the problem is how on earth do we calculate whether something is a rectangle without holes. And there's one pretty cool method that we can use to do that. Anyway, let's start by taking in our inputs. So how big is our grid? It's 12 by 12 characters, okay. And let's also just create a grid list. And let's do I in range 12. Let's take in our inputs and let's add that to our grid. But we also want to keep track of something else. And what I'm going to keep track of is I'm going to keep track of all of the coordinates of a symbol. And we'll see why we do that later. But for example, if I had this input, then I'd keep track of the 7 coordinates that have a hashtag in them. And the coordinates start from 0, 0 at the top left. And so let's create a dictionary that does that. And we want to go through for character in the row. And if the character is just equal to a dot, we don't want to do anything. So let's just continue and ignore that. Oops. And if the character is not a dot, then we do actually want to keep track of the coordinates, because the dots are irrelevant to us. We only care about the characters themselves, like the interesting characters. And so let's do in our dictionary y character dot append and the current coordinates, and that's just going to be I, which is the y coordinate, and the x coordinate is going to be, we haven't actually kept track of that yet. So to keep track of the x coordinate, let's just change that to that. Let's make that row char. Same thing here, row char and char. Okay, so now we're keeping track of our coordinates correctly. But of course, there'll be an error, because if, for example, that symbol, so row char is just a symbol, for example, it could be an and symbol or a hashtag or a plus. And so if row char doesn't already exist in our dictionary, it's going to throw an error, right? Because we can't append something to a list that doesn't exist. And so what we should do is we should import this thing from a library called collections, and it's going to be this command called default dict. And what this does is that when you define a dictionary, you can define it like this instead. And in this brackets, you put what your default value is. So in this case, list. And so essentially what this does is if this doesn't already exist in the list, in the dictionary, it's going to create that in the dictionary, and it's going to set the value to equal to an empty list. If, for example, I wanted it to be equal to 0, I'd put int, or if I wanted it to be equal to an empty string, I'd just put string. But in this case, I want it to be equal to a list. And so that's how we use the default dict command. It's just a bit of a cleaner way of achieving this, because you don't have to, like, if you didn't have that, you'd otherwise have to check, for example, if row char in y, then you have separate code to add it, and then you have this line of code. So this is just a bit of a nicer way of doing this, but the concept is not too difficult. Okay, so now we've inputted our grid, and we've also got a dictionary which contains all of the coordinates of every special character. Now let's do the actual computation, the actual calculation, and this is going to be the difficult bit. So we're going to go back to whiteboard, and we're going to figure out how on earth you can do this. And I would suggest, if you're doing this at home yourself, at least pause the video and maybe have a think for a few minutes, or maybe you've already had a think, but have a think for a few minutes and see if you can come up with a technique yourself. But anyway, so here, for example, this obviously isn't equal to, what is it called? It isn't equal to a super enemy, because it's not a proper rectangle with no holes, right? How do we know that as a human? Obviously, we just instantly look at the shape and we're like, that's not a rectangle. And why isn't it a rectangle? Well, if we were to take, for example, the bottom left corner and the top right corner, like that, then, well, if we were to kind of connect them like that, then we see that not all of these cells are filled in, and that means it's not a rectangle. Whereas, for example, if we had this, let me just refresh it because it's bugging out. Yep, so if we had this arrangement instead, then, for example, we'd look at the bottom left corner, the top right corner, and then if we were to draw that same shape around those two corners, we now see that this is almost a rectangle, right? Because there aren't any holes on the side, but there's a hole in the center, and so it's not a rectangle, or a square, I guess, in this case. But a square is a form of a rectangle. So now if we fill that center in, now it is a super enemy. And it's a super enemy because every single cell between those two corner cells is filled in. And that's the critical algorithm we're using, right? Because if we were to look up here, not every single cell between these two cells was filled in, and here it was filled in. And this also accounts for the whole issue as well, right? Because whilst you may come up with an algorithm that calculates that this is not a super enemy, it may be difficult for you to come up with an algorithm that calculates whether there's a hole or not. And so this algorithm is a good way of doing that, because it doesn't really matter where the holes are. They could be, for example, on the side, or they could be in the center of your shape. But this algorithm will still work because it counts how many empty cells there are between the bottom left and the top right corner. Of course, there'll be cases where the shape is going to be really, really irregular, basically. And we need to, like, for example, if I go back up to this one, and let's say that's a cell, and do that. So all of a sudden, is this our bottom right corner? I'm not really sure. Like, maybe this is our bottom right corner, bottom left corner. But either way, what we need to do is we need to draw a rectangle or a square that encompasses every single of our special characters, and we need to check to see if they're all empty or special characters or not. So what I'm trying to say with this edge case, for example, is that we don't necessarily know what the bottom left corner is, right? Like in this example, it was quite obvious because it was just the lowest down and the furthest left. But in this example, like you could feasibly think that's the bottom left or that's the bottom left. And so neither of them are actually the bottom left, right? This empty cell over here is the bottom left. And so we need to keep that in mind when you code our algorithm. So our algorithm, as we obviously just discussed, we need to find the bottom left coordinate and the top right coordinate. But since, as we again just discussed, like that doesn't always exist, right? There is no bottom left coordinate here. There are two bottom left coordinates. There's the leftmost and there's the bottommost. And then here there's a topmost and a rightmost, which both happen to be the same cell, right? Because this is the topmost and the rightmost. So what we're actually going to look for is we're going to look for the minimum x coordinates, the minimum y coordinates, and the maximum x coordinate and the maximum y coordinates, and that will give us the bounds of our rectangle, right? So in this case, we can obviously tell then like not all cells are filled in, but down here, if we were to calculate the minimum and maximum x and y coordinates, we'd get this corner and we'd get this corner, and then we should be able to just draw the bound around that and see whether all of those cells are occupied. And we want to do that for every single special character until we find the super enemy. And so let's say for special characters, so for character and coords in, and let's call a dictionary something more useful. What should we call it? Actually, no, I think y is fine. So for char and coords in y.items, we want to essentially find, as we just discussed, the smallest x and y and the greatest x and y coordinates. And so let's say min x is going to be equal to the minimum of the coord for coord in coords. So for each coordinate, but this is going to be like a coord is a tuple, right? Because as we've added it to the list up here, this is a tuple. And we only want to look at the x value in this case. And the x value is just going to be the first one. And so what this line of code does is it goes through every coordinate tuple, every coordinate pair in our dictionary for that given character, and it extracts only the x coordinate, and then it just selects the minimum one. And so as you can imagine, the code to calculate the max x is going to be this basically the same thing, but with max instead of min. And as you can probably also imagine at this point, the code to calculate those values for y is going to be a very similar thing, but with min y and max y here, just to change the variable names. And most importantly, we're now referring to the y coordinate, and so we have to change the indices from zeros to ones, because that's the y coordinate in our tuple. And so that's what we've done. We've got the 4 minimum and maximum coordinates. And now, how do we calculate whether there are empty cells between them? And this is the key bit. This is where you can either, for example, decide to try and go through every coordinate and kind of just simulate it, which is going to take a while to code. It's going to take a while to run, but I think because this is only a 12 by 12 grid, but there is basically no time issue, right? You can have really inefficient code and still get it correct. The time issue is not the problem here. The problem is that to actually write the code is going to take you a long time, and we're in a time pressure competition scenario, so we don't want to be doing that. And we've actually already done some of the work because we can essentially check, like we can calculate the width and the height of this rectangle bound, and therefore calculate the area. Once we know the area, we know how many special character cells there should exist within these bounds. And if that many special character cells do not exist, then we know there's going to be a hole, right? For example, the area of this red thing is going to be 4 times 4, that's 16. But we only see, how many of these? We only see 8 special characters here, and therefore it's obviously not full. Here, the area of this red square is 9, but we only see 8 special characters, and so again, this is not full. But if we were to like say this is a special character 2, now we see 9 special characters in our grid, and the total area for this square rectangle is 9. Therefore, this is a super enemy, right? And so let's calculate the width and height of our grid. Sorry, of our, what's it called? The rectangle of our super enemy. And that's just going to be, for example, max x minus min x, and that's going to be equal to the width. And then the height is going to be equal to max y minus min y, right? We're just taking this coordinate, and we're finding the difference between them for the x's, and we're doing the exact same thing for the y. What's the difference between these two coordinates? But because this is an inclusive system, it means we need to account for the fact that it's inclusive, basically. So, for example, this may be coordinate 4, and this may be coordinate 2, because like our arrows don't actually point to these, right? They don't point to the axes, they point to the square itself. So let me draw that a bit more clearly. So our coordinate is actually that cell and that cell and that cell and that cell, and we want to find the difference between these two cells. But for example, this is cell 2 and this is cell 4, and so if we just do the minus, oops, it's getting a bit messy. So if we just do the difference between these two cells, that's 4 minus 2, which is 2. But obviously our rectangle is more than 2 wide. And the same thing up here. If we just do, say, the difference between these two cells, we get 3 minus 1, which is 2. And so we need to account for the fact that it's inclusive by adding an extra 1 to each of our width and our height. Right? Hopefully that makes sense. So now we have the width and the height, and so now we know the area is just going to be equal to width times height. And we can check to see basically if area is equal to, well, let's do the other way around. So if the amount of special characters that exist is equal to the area, and what is the amount of special characters that exist? Well, that's just going to be the size of chords, right? So that's just going to be len chords, because when we've inputted our grid, every single time we've encountered a special character, we've added that coordinate to our dictionary, and therefore the amount of coordinates in our dictionary for that special character represents the amount of special character, like the amount of that special character that exists in our entire grid. And so we know that if this is true, then this entire grid has to be filled up. And if it's not true, then the entire grid could look like this, where it's not filled up, or the entire bound, so the red grid. And so if this is true, then let's just break out of it, because now we found our super enemy, and our super enemy is whatever char is at this point, right? Because we've broken out of the for loop, which means as soon as we find the super enemy, we don't look at any more special characters. And so the last special character we looked at is the super enemy, which is just char. Okay, now we've got to go ahead and print everything out. And this is the nice easy bit. So let's go for I in, or let's, I guess, say for row in grid. We want to print out the row, but of course we want to replace every single special character super enemy with just a dot. And so let's just do row.replace the special character with a dot. And we should be able to run that code. Yep, and that is 10 out of 10. Was I going to say anything else? Oh yes, so the reason that we know um, like this code will work, this algorithm will work, is because of this bit, right? It tells us what is a valid super enemy, or like no, it tells us what a valid enemy is, right? So it means that we don't have to like assume that maybe there are characters that fall outside of these red bounds that are the same character as the blue one. Like we don't have to assume that maybe there's a blue character somewhere over here on the grid, right? Because we're told that all of the characters are directly connected to each other. And so that's why we can just kind of count how many characters there are in total, because every character in total is already in our bounded grid, as opposed to having other random characters elsewhere.